Yeah.
All right. Let's see if I can figure out how to share the window correctly again. Okay. So you should see the slides. And without further ado, hi everybody. My name's Kelly. We did introductions, and today I wanted to sort of talk about from the past to present of concurrency, and then use the lens of Haskell, of course, because that's our meetup. So today's topic is threads, locks, STM, and async, a journey through concurrency with Haskell. I aim for this talk to be about 45 minutes, so I'll try to keep it within that time frame. We're going to walk through the evolution of concurrency primitives. We're going to use Haskell to illustrate the examples. It sounds like a lot of you, or I mean, it's the Haskell meetup, so we all kind of know Haskell. So none of these examples should be too mind-blowing. But I'm hoping to weave a story from, the beginning to now. But let's talk about why concurrency matters. Everybody's sort of heard the phrase "the free lunch is over," maybe, in terms of clock speeds. With Herb Sutter wrote his famous article about clock speeds plateauing and chip makers pivoting to multi-core. So that shift meant that sequential programs stopped getting faster for free, and you have to explicitly use concurrency to exploit modern hardware. Um, but concurrency isn't just about CPU parallelism. Servers are I/O bound. They spend most of their time waiting on network, disks, databases, and concurrency lets you overlap that waiting. So on the client side, users expect smooth UIs, even during heavy computation. And then these three forces, multi-core, I/O overlap, and responsiveness, are why concurrency is important. And so why Haskell for concurrency? Well, Haskell is a pure programming language. It also makes the invisible visible through its type system. So in most languages, any function can secretly mutate shared state and you won't know it. But in Haskell, the type system explicitly tells you, uh, for instance, in int to int to int, it literally cannot touch shared mutable state. It can't do I/O, it can't race. So the I/O type is the gatekeeper. A lot of us are familiar with that. And the only functions that return I/O something can interact with the outside world. So this is a huge advantage for concurrency. Most of your program is pure, and pure code is trivially thread safe. You only need to think carefully about the I/O parts. Haskell also has lightweight green threads baked into the runtime, which we'll see shortly. A little bit of the roadmap. We're going to talk about threads and fork I/O, sort of the most base version of this idea. Moving on to locks and how Haskell uses MVARs to achieve locks. Then we'll move into STM. That's the software transactional memory, sort of the middle ground between getting us from locks and MVARs to async and structured concurrency. And then if we have time, we'll sort of put it all together with an example. So part one, threads and fork IO. This is the foundation of Haskell concurrency. Um, Haskell takes a different approach than, say, POSIX threads or Java threads. Um, and they use something called green threads. And so how did we get to green threads? Well, in the 60s, we started with operating systems introducing multi-programming, which is just the idea of running multiple programs by time slicing a single CPU. POSIX standardized threads with P threads in 1995, and Java in 96 made threads a first-class language feature, but they were still OS threads underneath. OS threads are more expensive than the abstraction we'll see. They take about roughly a megabyte of stack per thread, and it's pretty heavy to do context switching to the kernel. So also in 96, concurrent Haskell introduced green threads with the fork IO and MVAR. Around 2004, GHC added its multi-core, quote unquote, M-to-N scheduling runtime, multiplexing potentially millions of green threads onto a handful of OS threads across cores, which is arguably years ahead of its time because Go adopted a similar model 5 years later, and it took Java almost 20, with getting virtual threads in 2023 with Project Loom. So what's fork.io? It's the mechanism we use for spawning threads. The simplest possible concurrent program example in Haskell would be fork.io takes an IO action and runs it in a new green thread. That's it, one function, and what a fork.io returns is a thread ID. Each call spawns a thread with about a kilobyte of stack, so it's an order of magnitude smaller memory footprint than running OS threads. And the runtime scheduler is preemptive at safe points, so you don't need explicit yields. The thread delay at the end here that you see is a bit of a hack just to sort of ensure that the scheduler sees these two threads. This is a very bare bones version of threading a real program. You wouldn't want to be this manual. And by not being this manual, we sort of introduce more abstractions to control processes through the type system. So we see this like little image of, multiple green threads can get mapped to an actual OS thread. And generally, this M-to-N model takes N green threads and maps them to K cores. It doesn't have to be like that, but generally, each thread, one per core at the OS level. But then multiple threads that we just saw in Haskell can get spun up onto one. And the way we enable this is by compiling GHC with the threaded option, adding RTS, and then the N flag to use all cores. Okay, so what's the trouble with kind of touching threads and not using any other abstraction besides that is we can create a counter, for example, fork 1,000 threads, increment it, but we're doing an explicit read, then a tiny delay, which yields to the scheduler, and then a write. This opens a window where many threads read the same stale value, then all write back the same incremented result, losing most updates. So essentially, without guards, all of these threads can read that value very quickly, add their value really quickly, but not know that another thread touched it, not waiting long enough, et cetera, et cetera. So what would essentially happen if you run this code is intuitively it says add 1 to counter 1,000 times, but in reality, 800 of them will add 1 to 0, and then the next 100 might add 1 to 2 or 1 to 1, and then the last 10 or whatever will add 1 to 2, and we'll end up with a value like 3 instead of what you would expect, which is 1,000. Okay, so we're moving up a level of extraction. We see how to spawn threads essentially without thinking about them. We introduced the idea of locks, and then Haskell's take on locks, which is the mvar. And the idea is to achieve mutual exclusion with locks so that programs don't peek at data or change data when they're not supposed to. And we'll see that this is going to run us into some problems if we aren't careful about it, or if we don't, again, introduce some more abstraction. A little more history. Dijkstra invents the first formal synchronization primitive, a counter you can increment, which he called a signal, and decrement, which he called a wait. And this primitive blocked when it hits 0. Hoare introduces monitors in 10 years later. 10 years pass again, and we start seeing a lot more abstractions like mutexes, read-write locks, spin locks, etc. And finally, in 96, GHC steps in and introduces something called the mvar with its concurrent Haskell. And Haskell's contribution, which is beautifully simple, is a box that is either full, which contains a value, or it's empty. Taking from an empty box blocks the thread, putting into a full box blocks the thread. And from this single primitive, you can build locks, one-place channels, barriers, and signaling mechanisms. It's Haskell's sort of Swiss Army knife for basic synchronization. So the API of mvar is creating one with a value. So creating a full one, creating an empty one, taking from an mvar and putting to an mvar. Finally, with the modify mvar, we combine take and put. We do it atomically. So you take from an mvar, you potentially modify it, and you put it back. And built into modify mvar is exception safety. So it atomically takes the value, applies a function, puts the result back. And if your function throws, the original value is restored so the mvar doesn't get stuck empty, which would deadlock every other thread waiting on it. We mentioned that we use mvar as a lock, but also an empty mvar could be used as a channel to act as a one-place channel in which a producer puts and a consumer takes. And so our original counter, which didn't manage its access to memory correctly, can now be corrected by using something called the mvar, which is sort of the next level from just grabbing raw threads. Instead of IOREF, we use an mvar of int, and each thread calls modify mvar, which atomically takes the current value, adds one, and puts it back. Because take out mvar blocks when empty, only one thread can be modifying the counter at a time. This is how we achieve the idea of mutual exclusion. And then, this program is always going to print 1,000. We use read mvar at the end, which peeks at the value without emptying the mvar. So the thread delay is still a hack for synchronization. But when we get to async, we'll stop having to manage and guess how long these processes take in between. Okay, so this one I'll have to scroll, but it's, let's see if I can fix that. There you go. Let's get the whole thing in frame. And this is going to be our example of a deadlock. It is a classic one. It comes up all over. It's definitely in the paper that Peyton Jones wrote about beautiful concurrency, I think. And essentially, two threads we're mimicking a bank account, and the bank account has a balance, and it can do something like a transfer, which says from one bank account to another one, transfer this amount. And you can see that we are using a lock. We're using locks, and the thread delay is just a little bit of making sure that it grabs the right lock. And then we take another mvar, and then we put from, and we decrement the from balance, and then we put to, and we increment the to balance, right? The problem is what happens when we try to do this twice and two bank accounts or resources, if you want to think of it that way, sort of catch each other when they are depending on a value that the other has locked. So thread one takes A, now empty, yields, then blocks on take mvar B, and thread two takes B, now empty, yields, then blocks on take mvar A. So neither can proceed, and we're stuck in a classic circular wait. And we've achieved deadlock. What will happen if you run this particular example, because it's simple enough, and the runtime, the garbage collector, after the garbage collector does a cycle, the runtime will notice that we hit a deadlock, and it'll throw a blocked indefinitely on mvar exception. But you really can't depend on that for larger programs. If the runtime can't detect a deadlock will happen, say, n chains down the road. Okay, so locks, their big problem is deadlocks. That is essentially not carefully managing which resources you lock and block on, causing the program to freeze. And a way that Haskell has introduced the careful management of memory is in a package called STM, or the software transactional memory. So A little bit of history about STM. STM sort of comes out of a hardware world. Tom Knight from MIT in '86 proposes hardware transactional memory. Harley and Moss formalized transactional memory in a paper. Shavit and Tui, first software TM, that is the first instance of getting transactional memory in software. But the breakthrough comes with, of course, STM in a paper called Composable Memory Transactions by some names you might recognize, including some of the ones we saw earlier. And so their key insight is that Haskell's type system can enforce that code inside an STM transaction doesn't perform side effects. Okay, this is critical if a transaction might need to be rolled back and retried. You can't have it sending emails or launching missiles partway through. Essentially, it's a abstraction that prevents you from doing irreversible procedures while maintaining a memory for what we'll see here. And that is in the execution model of how STM generally works. So you see the TVAR is the VAR that's going to replace the MVAR that came before it, before running just vanilla locks. You generally pass in do notation executions to atomically. And so what happens is at commit time, it validates that have any of the TVARs I read been modified by another thread since I read them? If yes, the transaction is discarded and rerun from scratch. If no, all writes are committed atomically, i.e. other threads see either all changes or none. So this is safe precisely because the type system guarantees no side effects inside STM. Rerunning a transaction that only reads and writes TVARs is indistinguishable from never having run it. So no IO inside an STM. Okay. And some of the primitives we'll see for STM, of course, I mentioned TVAR. You can create one, you can read one, you can write one, and then this idea of atomically, which allows you to run an STM transaction from IO. So this API mirrors the MVARs, but it's in the STM monad. And so our counter example that we saw earlier, we can fix this trivially with by passing modified TVAR counter +1 to atomically. Under the hood, each transaction reads the counter, computes the new value, and at commit time checks if anyone else modified it. If so, it transparently retries. No locks, no possibility of deadlock. It's not bulletproof, but it does address the sort of problem that people were seeing with programming with locks and on their own.
I have a question, if that's okay.
Yeah, sure.
You said almost or another adverb like that. Is that a reference to performance issues or something else?
We'll see. It's actually just a different version of it'll look similar in output, but it's a different version of the same problem. They call it live lock. Essentially, these things can create a bit of overhead, and so the longer you make them, the more likely they are to sort of spin forever by resetting themselves often.
Okay.
So that's the problem. They call it live lock, and we'll see it here pretty soon. We look back at our transfer example to expound upon the idea that another really powerful property of this STM library is it's not IO, and so we get composability. So this example was the one we used to demonstrate deadlock, but now that we're in the STM monad, no deadlock's possible because we're not taking any locks, so there's no order to worry about, and we can then compose these, and atomically we'll ensure that all of the transfers happen completely or they don't happen at all and they get retried. So those last three lines compose two transfers together into a single atomic transaction. Both happen together or not at all. So no intermediate state is ever visible to other threads. And arguably, this is kind of the whole point of STM. STM, the composability. STM transactions are now like Lego blocks. You can sort of snap them in and place them where you want, and the result is automatically a correct atomic transaction. A couple of combinators inside the STM library illustrate the idea of blocking and choice. Okay, with retry and or else having the signatures. First, we'll take a peek at the withdraw function that we write here. It reads a TVAR, and what it does is it checks if a balance is sufficiently large. So if the balance is too small, then we'll retry and hope that the balance changes. Otherwise, we'll decrement the account by the amount. And now to elucidate a choice idea, the idea of choice instead of just blocking is that, we'll run this function, and if the first one fails, then we'll just run the second one and worry about its results. So, or else gives you the choice, try this transaction. If it retries, try that one instead. And so that smart withdrawal example tries the saving account first. If insufficient funds, it'll retry and seamlessly fall back to checking. So you can sort of imagine creating a tree of these if you wanted, with a hierarchy of importance or possibility. So the type system is what enforces the safety. What STM does is it factors out the transactional memory from doing I/O. Obviously, this is a bad transaction because the signature is STM, but within it, we're trying to do a I/O action, right? We're trying to launch the missiles and then write to a TVAR, but this won't compile because the STM monad is not I/O. You can read write TVARs, retry and compose, but you can't do irreversible operations to the world, at least within the STM monad. Otherwise, you can't do a rollback. You can't do a retry. You've gone too far. So what is allowed in STM? Reading, writing to TVAR, retry, or else, and pure computation. And not allowed, it would be like file I/O, getting stuff up in the network, string, print, any I/O action really. So what are the trade-offs? We get composability, but we add overhead for these TVARs and read writing, because every TVAR, that belongs to a procedure has to report back when it's been touched or if its value's changed, and it's got to be stored somewhere. We don't get deadlocks, but like I said, there was the sort of other problem that it introduces, which is the possibility of live locks, where your procedures are just too long. So the longer they last, the higher chance of having to retry, etc. So it's a simple mental model to think of transactions as either done or thrown out, but the overhead is that, or sorry, rather the long transactions retry more often, and we get type safety, but with type safety we get restrictions. So that's always just a sort of this or that kind of what do you want argument. So how do we do it? Rather, how do we deal with the fact that there's no I/O? Well, the no I/O restriction is sometimes inconvenient. You might want to log inside a transaction, but the general pattern we use is to compute inside STM, extract the result, and then do your I/O outside. It's a design constraint, but it's the price of composability and safety. Okay, we made it to async. So this is sort of, probably you see this everywhere. Not a C++ programmer, but in Python, async await, async await, async await, everywhere you go. And we've covered shared state concurrency with MBars and STM. Now let's move on to a different problem. How do you structure concurrent I/O? How do you run things in parallel, collect results, handle errors, ensure cleanup? That's where the async library comes in. With a little bit of history about async, a lot closer to where we are now, maybe in 2004 and 9, we get some event loops, Nginx in 2004, Node.js in 2009. C# mainstreams it in 2012. JavaScript adopted promises, async. Oh wait, Python got async IO, and Rust built its async ecosystem. But Haskell took a different path. Simon Marlowe published the async library in 2012, but it doesn't add new syntax or a new coloring to functions. That's because Haskell already has a runtime that handles scheduling. Every IO action is implicitly async capable. The library just provides structured concurrency patterns on top of the existing threading model. So Haskell's insight is that you don't need async await syntax when all IO already goes through a runtime. The async library just provides structured concurrency primitives. Why not just fork IO? Well, there's three problems. We get silent exceptions. If a forked thread throws, the exception vanishes. The parent thread has no idea something went wrong. In a server, this means silent failures, requests that disappear into the void. There's no return values. Fork IO returns the thread ID, not the result of the computation. To get a result back, you need to manually set up an mvar, fork the thread, put the result in the mvar, and take it in the parent. Boilerplate, that's easy to get wrong. And there's no lifetime management. When should the child thread stop? What if the parent exit or throws? With fork IO, children are orphaned. The thread delay hack in our earlier example was a symptom of this because you're just guessing how long to wait. So the async library exposes some of these primitives. Async is like fork IO, but returns an async A handle, a future representing the eventual result. You can wait on it to block until completion and get the value or re-raise this exception. You can cancel it to send an asynchronous exception. And wait any lets you wait for the first of several tasks to complete. Wait both waits for two tasks and returns both results. So we have this little example of using async. We asynchronously pull data from two URLs, wait on both of them to complete, and then print the pair. All right, some structured concurrency patterns. We have three key combinators. With async, gives you scope to lifetime. So the async task is automatically canceled when the callback returns, normally or by exception. The thread can't outlive its scope, so there's no orphan threads. Concurrently, runs two actions in parallel, waits for both, returns both results. If either throws, the other is canceled and the exception propagates. This is the workhorse for our parallel input-output, or our I/O. And race runs two actions, returns whichever finishes first and cancels the other. The timeout example is the classic use case. Race the actual work against the thread delay. And if the delay wins, you know it timed out. Otherwise, the fetch wins and you have the result. The loser is always canceled. There's no resourceless leak. Map concurrently is the fan out workhorse. If you give it a function and a list, and it runs the function on every element in parallel, collecting results in order. This is one line to fetch 100 URLs concurrently. Compare this to Go's patterns, spawn Go routines, use a wait group, collect results via channels, handle errors manually, or Python's async io.gather, which needs async versions of everything. Here it's one line, it's exception safe. If any fetch throws, all others are canceled, and it works with any traversable. So think lists, vectors, maps, etc. And then a function from another library, but similar enough, is the pooled map concurrently. which is just the bounded version of map concurrently. It limits how many tasks run simultaneously, which is useful when you don't want to just let as much resources as possible run. So useful to put a bound on your the number of threads you want to spawn. So so the slide drives home why structure concurrency matters. So with concurrently, if the second action throws an error, and then three things happen automatically, the exception is caught, and the first action, fetch URL, is canceled, the async exception, and the boom exception is rethrown in the parent thread. The parent thread. Contrasting this with fork IO, the child thread would just silently die. The parent has no idea. Fetch URL will just keep the fetch URL and the other threads keep running, and it's wasting resources. So this exception propagation model means you can write concurrent code, the same error handling patterns as sequential code. Exceptions bubble up to where you can actually handle them. So no silent failures. Then there was this idea of colored functions. So like in Python, for this example, as we color our functions with the async and await keys, and you can't mix and match non-async and vanilla functions together. So for every function you wrote or write in your sequential programming, you have to rewrite using async await. Whereas in Haskell, we can just, rely on its beauty. So every IO action works the same way. If you want to run it sequentially, you just call it. Want to run it concurrently, you wrap it in concurrently, your async. The function itself doesn't change. There's no async annotation, no await keyword. The GHG runtime handles blocking IO by automatically descheduling the green thread. Your code reads as if it's synchronous, but it's concurrent ready. So you can take any existing IO function and parallelize its callers without touching the function itself. Convenient. So finally, we're going to put it all together with an example. We've covered the four main tools across the last 60 years, 50 years of concurrency's evolution: the fork IO, MVARs, STM, and the async library. And so here's just a slide for, quick reference if you wanted to decide when to reach for what tool, just depending on the level of complexity you want to get into. For fork IO, it's good for true fire and forget, where you don't care about the result or exceptions. Good for background logging, periodic cleanup, and it's rare in practice. MVAR, when you have a single piece of shared state, simple, fast, well understood, a database connection pool, a configuration that rarely changes. STM, when you have multiple pieces of shared state that need to be updated atomically together, bank transfers, game state, anytime that the answer to can this deadlock isn't trivially no. And async concurrently, when you want to run IO in parallel and collect results, API calls, file processing, any fan out, fan in pattern. And the race is good for timeouts, redundant requests, fire two, take the first, or any first one wins scenario. And finally, the retry or else, which is good for blocking until a condition is true in STM with fallback strategies. So the real world web scraper, which combines async and STM. We have a list of URLs to scrape. We use a tvar for the results list and a tvar for the set of seen URLs. The process function fetches a URL in IO, then atomically appends the parsed result in STM and marks the URL as seen in STM. We use the pooled map concurrently, which runs the processing across all URLs with bounded concurrency. The STM operations are thread safe by construction because no manual locking is needed. And we take notice that the clean separation of IO, which is in fetch URL, happens outside the STM, and shared state updates happen inside atomically. So this is the pattern. Do IO and IO, coordinate state in STM, structure concurrency with async. Another common pattern you might see is the producer consumer. And the way we achieve this is with a new primitive from STM, an unbounded FIFO channel called T-chan. The producer writes 100 items to the channel. The two consumers read from the channel concurrently, each processing items as they arrive. Read T-chan blocks via retry internally when the channel is empty. No busy waiting. And multiple consumers automatically load balance because each read T-chan is atomic. The race combinator runs the producer and consumers concurrently and stops everything when the producer finishes. The underscore variant discards the result. I mean, you've seen that before. This kind of pipeline, producers, channels, consumers, all composed with race and concurrently, is bread and butter for concurrent Haskell applications. Streaming servers, job queues, event processing pipelines all follow this shape. And then, a table comparing Haskell versus the rest, which you can take a peek at later if you'd like. But our key takeaways from this talk, hopefully, is that purity is a superpower. Purity is the first line of defense. Most data races are impossible in pure code, and Haskell gives you a lot of pure code by default. MVARs are your simple, fast primitive for single resource synchronization. Taking it up into STMs, the breakthrough, we get composable, deadlock-free transactions where the type system prevents you from doing anything irreversible inside a transaction. The async library gives you structured concurrency, scoped lifetimes, automatic cancellation, exception propagation, without needing async await syntax, which takes us to the no-colored functions. Every IO action works both sequentially and concurrently. So this is a huge ergonomic win that most languages still struggle with. Hopefully I convinced you that Haskell is better, stronger, purer, and easier to reason about using these sort of libraries that are all available that have developed over the last 30 years. Some further reading if you want. There's parallel and concurrent programming in Haskell, which is biblical in scope. And then some papers that I referenced throughout. And then links to those packages, async and STM on Hackage. So I want to take the time to say thank you to everybody for letting me take this hour or so to talk with you all. And I'd be happy to start a discussion if you'd like. But that's it for the presentation.
Thank you very much. It was great.
Yeah.
Thank you.
I want to mention one more thing about async that I love is concurrently implements applicative, and so you can kind of just rate things the way you rate other things, like if you use applicative do or whatever, and it forms this particular relationship with IO. There's a relationship between sequential things and parallel things in abstract algebra called a duoid. And I have a library for this kind of thing that lets you just basically in do notation, just do like you would normally do IO, and it will make all the parallel parts parallel using concurrently. But you just, you don't even think about concurrently versus sequential. If there's a data dependency there, it's sequential, and if there's not, it's parallel. Of course, sometimes when you're doing things in practice, you'll say read or create a file and then read from that or write to that file or whatever, and there's not an actual data dependency. So you can still explicitly use monadic operators to force sequentiality in those places, because that wouldn't get caught. It would just try to do it concurrently and be like, I can't write to this file, it doesn't exist yet or whatever. And anyway, so you can actually erase even already the stuff that Haskell's already doing better. You can get even closer and more generic with it, and it's really great. It is such a great language for doing this stuff in. So
Awesome.
thanks a lot for this talk, Kelly. It was good.
It was very
Thank you, sir.
good.
Thank you.
I liked it a lot. I have two historical comments. I don't know if I can be totally off on this. I believe that around the same time, 2005, when Haskell introduced STM, Clojure programming language introduced it independently. So there is a different construction. Obviously, they don't have a monad, STM monad, but they have software transactional. They had software transactional memory built into the language. And from my understanding is that completely independently from Haskell work, just the was introduced in that context, right? Clojure, it's a Java virtual machine programming language, kind of a Lisp family, kind of like scheme-like. The other comment, I have historical one. I can be also very wrong about it. So the somewhat different than async, right? Somewhat different than like promises and async away type of stuff is the continuation style programming, right? Which has been around since 1950s. And Haskell has continuation monad, and I don't know how old that is, but it was, I believe, featured in that seminal paper by Mogi in 1991, which introduced monads into programming. And Haskell pretty much done whatever they could, I believe, and implemented that, rewrote the programming language based on that paper in around 93. So I wouldn't be surprised if a continuation monad didn't date back to something like, early 1990s in Haskell. I may be wrong on that. But I wouldn't be surprised. So that's very powerful, somewhat different, right, than async await, somewhat different than async library, but very powerful abstraction for doing uh, uh, the kind of callback programming, right? Which was there for a very long time. You guys could tell me what I got wrong if you guys think this is not relevant. But yeah, the that two historical notes came to my mind. Kelly, this was wonderful, very nice presentation.
Yeah, thanks so much. I'm glad I had the opportunity to share it. And maybe it was a bit superficial, but I wanted to sort of touch the whole arc,
No, I think that's really useful because I do think that, like, at least in practice, if I'm working on code with somebody or whatever, I mean, everything is like, of course we're using, async and we're like handling things this way. And there's not a lot of that, like, I think it is important to see that, like, how did we get here and what trade-offs did we make, and those things. And so anyway, I think it's a lot of great context, regardless of if you're familiar with concurrency and Haskell and stuff. Either or both.
Did any of you actually use like continuation monad in like some project? I never did. To me, it was always like, hey, super cool, but I never really end up using it much.
No, I used call CC back in Lisping days, but I've never used the continuation monad in Haskell. I don't think I ever have.
That would be interesting actually too. I don't know.
There's that paper too, the Kant, the mother of all monads, or something like that. That shows how you can use it to implement any other monad, basically.
It's also continuation style programming is very kind of dangerous, right?
Yeah, exactly.
You can there's like JavaScript called callback hell. And they have somewhat different take on it. They have like mutating callbacks, which all I void, return void, right? So you need in Haskell. This is more functional take on the kind of continue on callbacks, sort of, right? But from the point of view that you have a power of monadic syntax, that your programming becomes, you kind of program a thread of execution, that seems like less crazy, right? Maybe, yeah. To me, that somewhat actually resembles async await to some extent, right? Because you're dealing with callbacks, but you're chaining them in a very sequential way. So, yeah, I never used that in real projects. No, I wonder what is like is it how commonly used is this construction?
Yeah, I definitely haven't seen it around much, other than I just linked that article, The Mother of All Monads, that talks about this. But yeah.
I was also curious if there's some any well-known libraries or anything out there in Hackage that use await async await and some like good examples of doing it.
Yeah, there's tons of stuff out there. Off the top of my head, I don't know anything particularly simple, but maybe Kelly, you you might know something that's accessible. I don't know.
What was the original, or what was the question?
Just
Have I
use
seen a
cases of async, like out in the Hackage or things like that that are using it.
I haven't seen it yet. In fact, we're in my personal work, I haven't even implemented async yet. It was sort of, that's also kind of why I was like, oh, I'll do this in 2 topics. Maybe eventually I'll actually use async by the time I get there,
Yeah.
because I could tell that's where we're going, but not yet. So sorry.
Let's see. So what's the I can't think what it's called now. The thing from Facebook.
Oh yeah. In fact, I think I might have a note about it.
Why can't I think the name is escaping me right now?
It's Sigma. It's anti-abuse system. Processes
Oh, that's
millions
actually a
of
different thing than I'm thinking of. But they're probably using it or using it all over the place. So
Yeah. So there's one. Sigma, Facebook and Meta put out Sigma. It's an anti-abuse system. It processes millions of requests per second using Haskell's concurrency primitives. So there you go. Maybe that one's accessible. I don't even know if you can still find it.
Cool, thanks.
So
Yeah,
in Holland and Hard we have this like a logic solver, which sort of writes programs or implements programs automatically, more or less. So the way it works is basically you want to sort of compute as much information as you can by utilizing existing we call these atoms. But utilizing, so you have set of functions from A to B, sort of, right? From A to B, from A1 to B1, from A2 to B2 type of thing, right? And by composing these functions in many ways, or just using them, you can sort of, this logic solver kind of builds up a syntax to populate as much data as possible, based on this existing kind of atomic basic ingredients, so to speak, right? And that becomes very expensive if you want to do it sequentially. So this feature that Greg mentioned, that you being applicative allows you to run things more concurrently. It's used heavily because some of these ingredients kind of can run in parallel, and the information is obtained faster. So we're using it in some very interesting ways. So Jason came up with this thing called concurrentish. And we have this concurrentish name used in the code base.
It's the second time that I hear Greg talking about duoids. In this context about concurrent programming, it's the second time that the selective applicative comes to my mind. If I still don't know what it is, I've read the paper about it, and I remember it kind of has something to do with this.
Yeah, what's that package called? How do I look it up on Hackage?
Selective applicative functor. I don't remember the name of the package, but if you look for that, you surely bump
I think it's called
into
selective. I think.
called selective. Yeah. Surely the class, the type class is called selective, and it's in between applicative and monad. So you have functor, applicative, selective, and monad.
Nice.
Oh, I linked to something, but it didn't link to what I thought I linked to. Because can you not? Let me see here. I just linked to the async package. I went to link to its reverse dependencies, but I don't know if you actually get a URL for that or it's just.
Let's see. Yeah, that's
yeah, I linked to the async package. If you scroll down on that page or whatever on the right hand column, there's like reverse dependencies, and you click the details there, and you'll see everything that uses it. So, Daniel, you were asking about what uses it on Hackage. It might look, and I mean, I haven't filtered this list. It's a long list of like 600 packages, so I don't know what in there is using it in a way that would be clear. But there is a lot of stuff on Hackage that's using async, and so there's at least places you could poke around and and maybe find. That's one of the things I like about Hackage, that reverse dependency stuff. I end up looking at that a lot for things.
Yeah, I've used that a lot too, and then I forget about it. So it's there. So, yeah, thanks.
Sorry, I wanted to ask, this is completely unrelated and going back to threading. I was wondering how exactly the threading model is implemented, specifically the scheduler is what I'm interested in. So I know I suspect that the scheduler is something like Erlang, Erlang's process scheduler, which I'm not like I don't fully comprehend how it works, but I guess I in my head I model it as having a mechanism to estimate the size of each process unit. So as it is processing, as it is, I guess, beta reducing, it measures how much a particular process has done. And then when that reaches a certain threshold, it jumps to another one. So it tries to be this kind of like fair scheduler, naive fair scheduler, which works if you're not doing IO. So does anybody like here know about how Haskell's process scheduler works and how it, or thread scheduler works?
I do not.
Okay, I guess that's homework.
Yeah, totally.
Yep.
Love to hear about it.
Also, another question. So I believe Haskell gives you an API to actually use operating system threads as well. The question is, why would you do that? Is it there for like some sort of old backward compatibility?
I mean, I can imagine that you might want to have implement your own,
or is
thread
it more,
management, or have other,
or maybe interact with OS threads in some different ways, because they're all threads. So you may have some C like, right, utilities for handling these. Yeah.
I have a sorry, Michael, go ahead.
Sorry, I can actually maybe chime in on that. I was working on like a FFI bindings generator, and I think one of the reasons why you potentially want to pin on a thread is if you're interfacing with C or some other foreign function where the other thing expects to be bound on a particular system thread. So that's one reason.
Yeah, that's what I was thinking. That's probably somehow related to the fact that you want to interact with OS threads.
Yeah, I had a question actually for Kelly. Would you mind sharing the slides again? And specifically, I remember there was a slide, and this is kind of a question about terminology, I guess, or something like that. And you had a slide where you said something was written about IO actions going through a runtime, already going through a runtime, or something like that.
Yeah, let's see if I can find it, and then we can talk about it. You said actions going through runtime.
Yeah, I don't remember the sentence exactly. Already through runtime, I think it was literally a substring of what was on screen.
Yeah, I think it was that we don't need a
Yeah,
separate async
I think it was the
primitive.
first page of
That's cool.
async there.
Oh, okay. Let's see.
Because yeah, right. Yeah, here.
Oh, yeah. When
Yeah,
you
yeah,
said
yeah.
right, Haskell's inside, you don't need async await syntax when all IO already goes through a runtime. What does all IO already goes through a runtime mean? Like what is this telling me?
That you're gonna have to peek behind the man in the green mask to find that one out. I don't know the runtime very thoroughly. We'll say it that way.
I have a thought about what I think this means, but I'm not positive. But so when you do an IO action in Haskell, right, you're not actually performing IO at that point. You're basically building up like a record of things that are going to happen, right? And it's only when you potentially call something like unsafe perform IO, or when your program returns an IO structure to actually be executed, that at that point, like the Haskell runtime sees all the things that are going to happen and has all that view of things. Doesn't have to worry about like, oh, this just ran like because you did something, and then like it just returns some result that's now being used. So because IO has been isolated as the way it has since whenever the IO mono was introduced, it can do that analysis that every other languages that don't have this kind of purity, this kind of isolation of it, need to tack on this additional stuff to say like, hey, we need to treat this differently and track this IO and like do this extra work, and that's why you have that kind of extra syntax for the async await stuff to basically get the runtime to do the same things that Haskell does for every IO action all the time. Does that make sense,
Yeah.
Enrico?
Roughly, yeah, I kind of see something. Yeah, I think I understand. Like you're saying when you write IO code in Haskell, you're basically writing a recipe for something.
Yeah, exactly. And that's the kind of bookkeeping that other languages are doing when you tag those functions as async and stuff. But Haskell's like, oh, we're already doing that for everything. We can just, take advantage of that later on, and you don't have to color your functions and do those things.
Yeah.
I think
So I guess the core things Simon Python jobs, right? IO computation when executed is going to do stuff, right? It's not doing it. It's when it's going to get executed, right? So probably that's what it is, right?
So yeah, it's not that I don't think that nothing had to change in the runtime, but it was more that we don't have to change the the user language in order to be able to do these things. They still had to make changes to make things asyncable, but I was at a different level and didn't have to affect the language.
If I look at that like async await in something like JavaScript or TypeScript, I had to actually write some code like that. I kind of look at this and I see you squint and you see a do monadic syntax. It's kind of a somewhat awkwardly implemented do syntax in JavaScript, right? Or whatever other language that comes in. So that's why I kind of think this is more like related to continuation monad, because it sort of allows you to thread callbacks in more sequential way, right? So there's like we don't need a single wait because we have a do notation.
Right. It's like another case of programmable semicolons or whatever, where it's like everybody has their own syntax for every different monad, and
this is kind of one of syntax just for a single wait. It's not generalizable to anything else.
Yeah. Although in this case, it's more applicative than
Well, no, I think
monadic,
await is actually monadic, because what you you need when you await, you're basically saying, hey, I'm doing it
right.
sequentially,
That's your data dependency. Yeah.
right? Um,
I
so
tried to explain monads to our coworkers today because I guinea pigged them with this talk.
and
And I was like, well, and then I realized who I was talking to, and I said, they're boxes, they have contents, you can chain them together, and they can depend on previous values. And they're like, okay. And then I was like,
so I had this pleasure of having a heated exchange with Bartosz Milewski when he was writing, well, before he even contemplated of writing this,
Category theory book.
this book, right? He basically was saying, I have the idea of explaining category theory to programmers. And how do I explain monads in intuitive way? And he was like, very strongly opinionated. This is not a box.
yeah.
I don't want to say it's a box.
I
Give
know.
me other ideas. So
yeah, what else are you gonna call it though? I mean, how else do you explain it to people? How else do you simply conceptualize it? I mean, it makes sense if you can like follow math notation, but that always seems like the easiest reach. To say that they're containers, that they chain, and that they depend on each other. That the idea is you sequentially compute, possibly being dependent on previous data.
Then it's difficult for this the explanation to kind of for the person that listens to the explanation to then realize actually there's so many different monads for which the idea of sequentiality it's not really important or it's not relevant, or the idea of whatever, there's so many different monads
of container, right? Is async a container? What does it mean?
Yeah. Yeah.
One thing I remember, I think, from the book, the Bartosz book, is that he makes a kind of an explanation of why understanding the monad is so difficult. And his point is coming up with an explanation of a monad is the same thing as expecting that you understand that the solution to the following question is duct tape. And the question is, what is that thing that allowed fixing the Challenger something, the spacecraft, and at the same time fixes the piping of your house when something leaks, and something else. And you have these problems which have nothing to do with each other,
right?
They are all solved by the duct tape. And how can anybody work out that the magic is the duct tape if you just tell that what the problems to solve are? And that is Bartosz's way to convey what is known as the monad fallacy, I think, something like that. Of how can you even try to explain monads? Anyway.
Yeah, I feel like I always go from the generalizing from examples like error handling and IO stuff, and then starting, find another example like either writer or reader to kind of see how you can do these same things in some other context, or state's a great one to then move to or whatever. And but then you just say oh, we wrote some code that does this, we wrote some code that does this, what are these things doing here? It's here's how we're basically causing these things to happen in an order, right? And then you can kind of start extracting out the different things that happen in there. But yeah, it's hard to get to that general notion. Even there's so many things that you'll see even in the Haskell world where sure there's a monad instance or something, but then the library will still expose different names for all the monadic functions, for that are specialized to that monad, just because it's oh, no one's going to think about what does bind mean for this weird construct that I provided. It's okay, I've given you this function, just call that, and you're you can read it and know what it does, instead of just seeing a do notation and be what's happening in this chain of things. So even in the Haskell world, I think that comes up a lot, like
Yeah.
where it's like we're not, yeah.
I think you can look at simply as a pattern that is occurring very frequently, right? And like is RESTful programming a container? Do you need to come up with this weird intuitive half truths, right?
Well, yeah, and I also think that you can kind of abandon
Why?
it once somebody gets it and wants to
Right.
understand it deeper. You know, you're right, but often enough, maybe where you and I have disagreed, and I still see it this way, is that functors are very container-like. Functors are special containers that you can transform, but really they represent containment.
To me, they're not.
Yeah, exactly. Yeah, we totally see it differently.
Like the way I learn about functors is by studying algebraic topology.
Yeah, so you saw it in a different.
You basically take topological things and you move them into algebra, and you create this interesting thing where you can use algebraic from your knowledge about algebra to talk about geometry.
Topological objects.
Geometry, effectively, right?
Yeah.
And vice versa, right? You have now we have geometric intuitions about things that you notice in algebra. To me, it's like a polymorphism on the next level, right? Yeah, different disciplines, and you have some category, structure preserving transformation, which means they're kind of the same, right?
Yeah, up to isomorphism.
So that's the functor. Is it a container? What does it mean for it to be container if it moves, topology into algebra?
Nothing, but I do think that the Haskell functor, the Haskell category theory, is less general than the mathematical category theory. But I mean, it's not a strong opinion.
Because they're endofunctors, right? The
endofunctors in Haskell, like
they're map types to
types.
types. They're map types to types in a very specific way, also. But
maybe that should be the next talk, is algebraic topology.
No, I mean, unless you want to, unless you want to present one.
If you can program it, I would watch it. I mean, I like math. That's how we all got here, right?
Right.
There's no Haskell without math.
Yeah, kind of hand in hand. Well, guys, I'm probably going to jump off here in a little bit.
Yeah, no, I think I stop recording because I think there are no more discussion, right?
That's good. Yeah, thanks a lot, Kelly. Obviously, we